morning by Javier Rendón, please.
Good morning, everybody. I'm Javier Rendón from UNAM in Mexico. I will present this work, which is titled Pion Mass in a Magnetized Medium. This work was done in collaboration with Alejandro Ayala, Luis Hernandez, Santiago Bernal, and Jorge Medina, which are here in the audience also. So I will first talk a little bit about a brief motivation. I will then also talk about the state of the art for this kind of observables. Then I will particularize to an effective model, which is called the linear sigma model with quarks. And with this model, we will make an analysis of these kind of observables, right? The pole mass of the pion. Then I will present preliminary results, and finally, I will make a summary and perspectives. So first, the motivation. Why to study magnetic effects on the masses of pions, for example? Well, the first reason is that electromagnetic fields provide a powerful proof to explore the properties of the QCD vacuum. Okay? The other important reason is that since the dynamics of chiral symmetry breaking is dominated by pions, you better study the properties of pions on their magnetic fields, right? So in the work, we will particularize to the pole masses, but you can also study the so-called screening masses also. And we will study this observable, the pole mass of the pions, in the linear sigma model with quarks, and we will study both the neutral pion and the charged pions, okay? First, we are in the regime of non-perturbative QCD. So we need to try to solve the problem using alternatives, right? For example, effective models or lattice QCD. Effective models, you have several of them. For example, the Nambuyo-Nalacinio model, chiral perturbation theory, and the linear sigma models, which is the one I will talk about in this presentation. So now the state of the art. What has been done previously on these observables? Well, there is this, for example, this work done in the Nambuyo-Nalacinio model, in the SU2 Nambuyo-Nalacinio model. And here they plot basically the normalized mass of the pion as a function of magnetic field, right? And the general idea is that the mass decreases as a function of the magnetic field. We have this other result, a newer one, from several of the same authors, in which they plot also the pion pole mass as a function of the magnetic field. But in this one, they give a profile to the G constant, to the G parameter, right, of the model. And they fit pretty well the lattice results, which are shown here, taken from this reference. Okay. There are also results for the charged pions, and here are some of them. This is not directly the mass, but the lowest energy of the charged pions, right here, and also the pion mass of the neutral pion, and of course lattice results in dots here from these two references. There are also results from chiral perturbation theory, which can be shown here. This is chiral perturbation theory. This is the Nambuyo-Nalacinio model particularized to SU2. So the qualitative behavior is the same. It's a decreasing function of the magnetic field. There are also results from chiral perturbation theory for the charged pions, and all of them agree that the behavior is increasing, the opposite to the neutral pions, right? Okay, so what do they do, basically, in this kind of models? In the Nambu-Jones-Lacinio model, they don't have like the mesons as degree of freedom. So they make this approximation called the random phase approximation, in which they take into account this effect that the mesons are not strictly degrees of freedom. So they find the masses by finding this, solving this pole equation, okay? So this is basically the polarization function, and this is the propagator in the Schwinger propagator. So as I told you in the previous slide, they solved, for example, the neutral pion mass with this equation, where this self-energy has to be regularized. So they basically arrest the vacuum from the self-energy, but they compensate with this regularized function, right? So, and they have to be consistent also with the gap equation, and that's basically everything they need to construct the pole masses. For the charged pions, basically the same idea, but here you have to be very careful taking into account the Schwinger phase, okay? But the procedure is exactly the same. You just need to account the Schwinger phase. You need to solve this pole equation with where the self-energy has been regularized, and that's all, basically. So why to choose another effective model besides the Nambu-Jones-Lacinio models? Because the more effective models you have, the better, right? To compare with lattice QCD. So in this model, the linear sigma model with quarks, you have the mesons as explicitly degrees of freedom. That's one good point. And it is also a renormalizable model. And well, the model basically is constructed with this symmetry breaking pattern, okay? And this is the prediction for the masses of the model, okay? So you need an explicitly breaking term to construct the pion mass also. So the model predicts interactions. For example, the boson-boson interactions are here. It also predicts fermion-boson interactions, which are here in these vertices. And okay, now to construct the self-energy, you need a bunch of diagrams, right? For example, for the pions, you need these diagrams if you want to construct the self-energy, the complete self-energy, okay? You need these kind of diagrams to construct the self-energy for the fermion. And finally, for the sigma, you need these diagrams, okay? Okay, so to construct the self-energy consistent in the model is like a little bit involved because there are many particles and many coupled equations, right? But this is the thing that needs to be done, okay? So this is the self-energies written explicitly here. Okay, so as a first approximation, we will take input from other models just as a first attempt, right? Because as you see, the model is quite complicated to solve it like fully, and it is a work in progress. But as a first attempt, let's take masses from the Nambu-Jones-Lacinio model, for example. So we take as input these masses from the Nambu-Jones-Lacinio model for fermions and play with them. The prediction for the G parameter of the model in this case is this number. And from all the Feynman rules that I told you at the very beginning, we will particularize to these vertices, which is the vertex of a pi 0 and quarks. Quarks up or quarks down. And you also need the Schwinger propagator, right? The Schwinger propagator, in the limit of the magnetic field going to 0, correctly describes a usual fermion propagator. So the first diagram is the neutral pion surf energy, the fermion contribution only is given by this bubble. And the Feynman rule for this bubble is basically this, okay? This can be diagonalized in the momentum space with no problem. So that's pretty much everything, okay? For the charged pion, as in the Nambullino-Lasinio model, the momentum space is not appropriate, so you need to work in coordinates, right, because of the Schwinger phase, and this is the self-energy in this case. Okay, now we need to regularize also, because the vacuum explodes, right? So we need to subtract the vacuum. This is the way we regularize. For example, the pion mass, the neutral pion. And we solve explicitly this equation to find the masses. Okay. The same thing with the charged pion. In that case, we subtract the vacuum also, and we solve this equation. Okay. Here you don't have the perpendicular, as you see. You don't have the perpendicular components of the momentum, right? Instead, you have this Landau level. So for the neutral case, we basically have some plots as a function of, for several values of G. And this is an interesting thing. If you plot the vacuum value for G, the results are not pretty good. And as soon as you start decreasing the value of G, you start obtaining better and better results. That's the idea. For a result, for a value of G of this number, 0.33, you obtain quite good, quite decent qualitative behavior if you compare with the lattice QCD results or with the Nambullino-Lasinio results. So here I isolate the better result we had, right? The curvature is not the right curvature I present, but there's plenty of space to play with the parameters, right? We have tadpoles, and we have other masses. But qualitatively, it is a decent result if you compare with other effective models. For the charged pion, you obtain this kind of plot, okay? An increasing function, an increasing with respect to the magnetic field. And again, this is not exactly the mass. It is the minimum energy, if you want to see it like this, okay? So basically, that's the preliminary results, and here is a summary and perspectives, okay? So we have calculated the neutral and charged pion self-energies in the linear sigma model with quarks. We have obtained preliminary results for the pole masses for neutral and charged pions as a function of B. And we have compared the results with lattice QCD and Nambullino-Lasinio, and we have a qualitative agreement only, and this is important, when there is a magnetic field dependence on the coupling G, okay? Here we are not finding a profile for this G, right? We are just pointing out that the G value needs to decrease, and decrease fast. That's what we are observing. Perspectives. We need to complete the calculation in a full consistent way with the linear sigma model, because as I told you, this was a first attempt, and we are borrowing some of the masses, for example, the fermion masses, from the Nambullino-Lasinio model, okay? So this needs to be carried out in completely within the same model, within this model, the linear sigma model with quarks. And finally, we will add thermal effects to the analysis. And that's basically everything. Okay, thank you very much.
So, any questions?
Thank you, Javier, for the talk. So as I understand, the G, that is the coupling with quarks,
Yeah.
you fix it to improve the behavior, magnetic behavior, but Isn't G fixed already in vacuum?
Yes, it is.
So
It is fixed in vacuum. And if we plot the value for the Fermi mass, you obtain this value for the G, which is huge, right?
It's huge, yeah.
But if you try to solve the problem with this value of G
Yeah,
from the
no,
vacuum,
it drops
you
down.
you find ridiculous solutions, like it just drops off very
And
quickly.
there's not any window in vacuum to change the couplings and the constants, whatever you have involved to play with, or
Yeah,
this
I have other ingredients which I have not touched, but for example, we have another parameter, right? The lambda parameter
yeah.
with mesons. So I need to fully take into account the other masses within the linear sigma model with quarks, not borrowing from Nambuyuna-Lassini, for example.
Yeah.
But qualitatively, it is good, more or less. Yeah.
So, any more questions?
Thank you, Javier. I mean, for a few days ago, Norberto Scoccola presented his new results for the pi-zero evolution.
Yeah.
How do
Yes.
you compare?
Yeah, they are compatible. Well, these are the Norberto's results.
But this is for the charge pion.
Yeah, for the charged pion, the focus here is for the charged pion. So, but for free, he gave us also the neutral one.
Yes.
Here is difficult to see, but it decreases.
Okay.
Okay. Here you can see it more nicely. Zoom it with more zoom, right?
Okay. Thank you. Thank you.
Thank you, Javier. Just to add a little bit of information that perhaps goes in the direction of Christian's question, can you go to your summary
Yes.
slide? I think that what we've been discovering or chasing after some time already is to understand why the couplings, lambda, G, and the parameter A in this model change with the external conditions, in this case the magnetic field.
Yeah.
And the way you are putting the problem or setting up the problem can be phrased in a language in which what you are saying is that you have mixings. The magnetic field induces mixings between the masses.
Yes.
So the neutral pion mass will depend on the charged pions through your diagrams that involve those masses in the loops. Also will depend on the fermions and so on and so forth.
Yeah.
But if you want to respect the form of the mass given from the original Lagrangian, which is this that you're showing here, then because the masses will evolve with the magnetic field and also the vacuum expectation value will do, then it is natural that if you now translate those masses into the evolution of the couplings and the parameters of the model, then you have a nicer way to compute self-consistently the changes in these parameters. And therefore, it's not surprising that to describe the evolution of your mass as a function of the magnetic field that you showed in the previous plots, you require that the coupling changes and so on and so forth. So I think this is a natural way to see that those couplings are not fixed or God-given in vacuum, but that rather they evolve as a function of the magnetic field. So this is just a comment to maybe clarify what Christian was asking.
Yeah. 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 Thank you.
Just to complement or go along with the remark by Alejandro, what we have done was something in that line. We considered the Nambu-Yonah-Lasinho model and then calculated fully self-consistently depending on the magnetic field. So if you go to one loop polarization, like you do, you obtain coupling constants dependent on the magnetic field, masses dependent on the magnetic field, everything at once self-consistent. So these mixings, they will, between masses and quark masses and meson masses, they will appear, they naturally appear if you do that.
So, any more comments or questions? If not, let's thank the speaker.
Okay. Can you hear me?
You can go.
Yeah.
So, now we have José Jorge Medina Serna, please.
Thank you very much. Good morning, everyone. Bom dia. I would like to talk about some work we've been doing in Mexico in the university, in the Autonomous University, National University of Mexico. It's a work that is in collaboration with Alejandro Ayala, Isabel Dominguez, Maria Elena Tejeda, and Yvonne Maldonado. And it has to be about the relaxation time for the lambda hyperons to align its spin along the angular momentum or the vorticity. So I would like to start. Okay. As we know, and as we have talked along all the week, non-central heavy ion collisions produce a vorticity and an angular momentum and angular velocity that induce several effects in the system. Particularly for me is the polarization of the lambda hyperons. That is an observable that was first observed in 2017. And there is a lot of approach to estimate the polarization of the lambdas. And we would like to explore this one, in which we separate the collision region in two zones. The first of the zones is a dense core dominated by effects of the QCD, and a less dense corona that the effects that dominate that region are more like reactions to, for example, proton-proton collisions. So we use this idea to separate the two systems to calculate the polarization by, well, just putting all the lambdas aligned minus the lambdas anti-aligned divided by the total number of lambdas produced in the collision, and we will have a global polarization. Okay? But we can separate, as I did here, no? QGP aligned and QGP anti-aligned, that are the lambdas coming from the core. Here are the lambdas coming from the corona, aligned and anti-aligned, and with a little bit of algebra, we can get this equation here, where we define these two objects that are intrinsic polarizations. And is a measurement or an idea of how much tends to align the lambdas coming from each region, and depends on the kind of reactions there. So this allows us to separate the global polarization into contributions, one coming from the core and another one coming from the corona. And this idea has had success for estimating the polarizations as a function of the energy collision, but it also has had troubles estimating the polarization as function of centrality, and this will be the main result I will show. So let's talk about how we are going to model the two regions. First, the corona, dominated by QCD effects. We can estimate the self-energy of strange quarks produced in the core, where we expect to have QGP. And we will put all the information of the spin to the quark S, and we expect that the spin of the strange quark will transfer to the lambda after hadronization. So we use a hard thermal loop approximation for the gluon interacting, and all the information we'll put in the fermion, in the quark. We would like to do something like this for the corona, but there the interactions are more, it has less energy, so we have to use an effective model where the particle that will mediate the interactions will be the meson sigma. And also we will put some information about the thermodynamics of the system, finite temperature and chemical potential. So, but we need to be careful about the temperature because it's not high. So, okay, having this, the intrinsic polarization can be obtained in means by the relaxation time. The relaxation time is the time that it takes to the lambda to align or anti-align. And if the system leaps large enough, the system will be polarized. If not, if the system lifetime is short, then the intrinsic polarization will be close to zero. And the relaxation time is closely related to the production rate. Again, that is in terms of the self-energy that I showed before. And I showed this plus-minus sign because the propagator in rotation that we use for the fermions that contains information of the vorticity and the spin naturally separate an alignment part and anti-alignment part. Also, it is interesting to see that the angular velocity enters as a chemical potential coupled with the spin, of course, no? Plus and minus. So finally, having these two production rates or alignment rates, we can calculate the difference, and this will give us a kind of polarization rate or something like this. Obtaining this rate, this polarization rate, we can obtain the relaxation time as the inverse. So let's get started. By the effective model we want to use to model the corona is the relativistic beam field model, where we will have a nucleon part, a lambda part, and the sigma part. And the thermodynamical corrections, we will implement this self-energy of the sigma, where these two fermions are nucleons. For this simple model, we are just considering finite temperature and chemical potential, not vorticity in the correction here. So the details of this calculation, you can find it in this article. But at the end, in approximation where the temperature is not higher than the nucleon mass, we obtain this correction. It's kind of long, but we put it in the propagator of the boson, and we defined an analog of the thermal, well, it's not an analog, it's a thermal mass, a factor we call gamma t, and well, this x is just the coefficient of energy and momentum. Well, now I just talk a little bit about, we can separate the imaginary and real part explicitly of this propagator, and that allow us to write in easily the spectral density. Because we need the spectral density to calculate the self-energy of the lambda. And that's what I show here. I will not enter so much in details. This part of here, you can check it in this article. The calculations for the sigma and the lambda part it's simple because the coupling is scalar in a difference that is vectorial. But they had things in common. First, the angular velocity enters as a chemical potential in both results. That's very interesting because this immediately will produce more aligned fermions than anti-alignment because the sign that enters as a chemical potential. Also, the angular velocity enters in the region of integration that appears as the kinetical conditions, and the effect is just to shift the integration region as a shift in the energy. So that is what they two models have in common. And the difference, well, this is a model where we use a chemical potential of quarks. Here enters the baryonical potential. And of course, the coupling and the masses that enters here are different because different particles. Well, with these two models, we can estimate polarization, as I showed before. And to do that, we need to obtain parameters. First, we need to know the volume of the system because the reproduction rate or the alignment rate depends on the volume. Well, we made a deep search in that kind of studies, and we find this article from WACAS that makes an estimation of different parameters of volume and expansion of velocity of expansion as function of centrality. That's exactly what I wanted. And just in the energies that I want to analyze, that is 3 GeVs for gold-gold collisions. So for the core is a different thing because usually the results are for all the systems, expecting that all the system is core. So just for a preliminary result and observe how the difference in the two regions, core corona, affects global polarization, will you just assume 1% of the total volume of the system as QGP. That is reasonable because we expect just little drops in the huge hadron cloud in that kind of energies. Also, we need to estimate the angular velocity. Well, there is a study that did that with some simulation of URQMD. And also, we need to have an estimation of the chemical potential that comes in this parametrization from here. And finally, the last ingredient we need to have some preliminary results are these parameters of the relativistic mean field model that they were obtained by scattering in, well, this work here. Finally, there is another ingredient we need. That is the number of lambdas produced in core and in corona. And we use this model that is a Bjorken model. We have a density. Here, density of participants that depends in these thickness functions that are in terms of this Wood-Saxon distribution, okay? But there is a key concept here that is the critical density. The critical density of participants will tell us if we produce or not produce lambdas from a core or if we have a QGP. If the density of participants here is lower than the critical density, these Heaviside cuts the production of lambdas, and then we don't have lambdas from the core. And the other side, we use a similar idea with the critical density, and when the density is lower than the critical density, then this heavy side will activate the integral, and we will have lambdas from the core. Oh, I have a typo here, I'm sorry, this should be the index for the corona. Well, we use these two parameters. You can check the details of these, the details of the fits of these parameters in the articles. Then we have all we need to calculate polarization, and I would like to start with the relaxation time from particles coming from the core, in this case, strange quarks. As we see, as a function of impact parameter, we see that the relaxation times decrease as the impact parameter increase. That's because in our models, the angular velocity increase with the impact parameter. So for most central collisions, the relaxation time is around what, 3, 4? For this temperature of 90 MeVs, and for 100 MeVs is kind of lower. We can see that the relaxation time decrease as function of temperature. This is for core region. For corona region, the relaxation times are huge. That's because the model we take where the temperature is lower than the mass, it puts a high suppression factor that comes like an exponential, rises to the minus m of the mass of the nucleon divided by the temperature, so this is high suppression. But we see that decreases rapidly as a function of impact parameter, but still is huge even in the highest impact parameters here. Then if we calculate the intrinsic polarization using these relaxation times, we can see that the lambdas coming from the core polarize very, very soon for in the mid semi-central collisions. We have a high intrinsic polarization. In the other side, intrinsic polarization for the lambdas coming from the corona is lower, so much lower. That's because the high relaxation times. Okay, so around in the most peripheral collisions, we have something about 0.0.1 because in this axis we have a factor of 100. Okay, with this in hand, we can now analyze the global polarization contributions from core and from corona. From core, even despite we have a high intrinsic polarization, the number of lambdas coming from the core is so small compared with the lambdas coming from the core. That's because we have a very, very small core region, and then the polarization has just this hump, and then decays to 0 for very low centralities, not even close to 50 or 15 or something like that. But it's interesting in the case of the corona, because the corona is very sensitive with the temperature. We can see this small variation between 190. This is this huge region. But we see here in the most peripheral collisions, the model estimates a huge polarization in the order of the experimental measurements. This is because the contributions for lambdas in the most peripheral collisions dominates over the corona production. We see that corona or QGP is not formed around here, And all this global polarization from corona is dominated by the intrinsic polarization we obtain. And then we can put all these ingredients together and find this result. We see this little hump in the most central collisions, and that's all the contribution that core does to the global polarization, because then falls to 0. And then we have all the contribution from corona. So, in summary, well, we have this core corona model, and this model allows us to separate the two contributions from polarization, and these two contributions are differentiated for the kind of process that dominates in each one. So we can estimate a global polarization from one region and from the other. The intrinsic polarization is the key ingredient in their model because it has the information of obviously the relaxation time, but also the kind of process that dominates in every region. Then we could obtain an estimation for the relaxation time of the quarks, strange quarks, and if we transfer that polarization to the lambda after hadronization, well, this is the global polarization of the lambdas, the emitted lambdas. We see that the relaxation time of the core is larger than the relaxation time from the corona, because the interaction are so much stronger in the core. But it's not significant for larger centralities, at least at this kind of systems, because the region of corona dominates all the volume of the system. And we could put a boundary to polarization of lambdas in a two set of parameters, and at least in a range of temperature from 90 to 100, we obtain an estimation that is that bounds the experimental measurements of the lambda polarization. And so these are our main work that we developed in the recent months. There is still a room of improvement, but we are optimistic that this model will provide us an estimation of polarization as function of collision energy and also as function of the centrality of the collision. And I want to thank you all for your attention and your questions.
So, any questions?
Thank you for really a very interesting talk and kind of amusing to see the course sort of kick up at the low end. So it sounds like you're going to look at this as a function of energy. Do you have a sense of how much it's going to change things and how much the corona is going to change things as you get to 7 or something like this?
Yes. Probably for high energies, the corona contribution will be almost 0 because it's highly suppressed by a term that depends on the mass and the temperature. And also the chemical potential. For higher energies, that the chemical potential is lower.
Well, that's true when that's a generic statement as you go quite high, but still the chemical potential is still high at 7. And actually does one...
7.
Yeah, so if I think about 7, first of all, I'm really glad that people are paying attention a little bit now to the 3 GeV stuff. It often gets kind of ignored. I think it's important. But is the core really much different temperature as I get to 7 or even higher? Or the core temperature depends so much on root? I meant to say corona. Is the corona really so much higher temperature at, let's say, 7?
I think it will affect, of course. For that mid energies, now there will be this competition.
Right.
No doubt. But will we have this competition, but eventually the corona will fall.
Right.
But at these mid energies will be very interesting to analyze the corona contribution, no doubt.
Yeah, it'll be interesting to see. Thank you.
Thank you.
Any more questions? Okay.
I just wonder if the corona part of the physics, the polarization, similar to PP, that can you is there some comparison can be made with PP collisions?
There was some analysis and fits that that how to say it, that I agree with that statement. I don't show it, but as I remember, the fits are good. So let me go back a little bit. I don't have it in a backup. Yeah, this comes from this here in the thickness function. For the corona, we change here this parameter of the sigma. Forgot the name. It's missing. But yes, we have an estimation. We can check it in this reference, but I don't show it. The fits that I agree with that statement.
Okay, any more questions, comments? If no, let's thank the speaker again.
Thank you, thank you.
So now we have a talk by Luis Alberto Hernandez. Rosas, please.
Okay, everybody can hear me? Okay, that's good. Oh, well, first of all, I want to thank to the organizers, Anna and Giorgio, for the invitation and for organizing this beautiful event, this conference. So thank you for the invitation. And today, I want to talk about some phenomenon that is very good understood, that is the inverse magnetic catalysis. But it's not because I will present something new in the sense that some new results. I will present some new techniques that maybe can help us for the future to understand better other phenomena or provide new information about other external phenomena that happens in heavy ion collisions or some other systems where the Stirling interacting matter in extreme condition exists. Okay, so here is the content of my talk. A brief motivation. I will show some results that we had in previous years. After that, I will show a first attempt to find the inverse catalysis with some effective model, that is the linear sigma model. I will show some troubles, and we will tackle again the problem and check if with new techniques we can find a better results. And well, at the end, I will show the analysis, the results, and we'll talk about future works that we are planning as a group. Okay, this is the first slide. Why to study this kind of magnetic effects? Well, we know perfectly that some physical systems exist in nature, and some experiments can produce strong magnetic fields, strong enough to consider in the regime of low energies of QCD or strong interacting matter. The model that I will use is the linear sigma model. Javier talked a little bit about the features of this model. It's an effective model for low energy QCD energies. It's a renormalizable model. The symmetry that we kind to analyze is the chiral symmetry. It's a symmetry spontaneously broken. And this model involves quarks and mesons in the analysis, and that is good for the purpose to see what happened with the phase transition in the presence of a magnetic field. Here is the Lagrangian of this model. Okay, we have sigma meson, 3 pions, and fermions that in this case are quarks. Okay, but I must say that we have 1, 2, and where is the other? 3 free parameters in this model. This squared mass term that appear at classical level in the Lagrangian, and 2 coupling constants. This is the self-boson coupling constant, and this is the constant between, or the coupling constant between the fermions and the bosons. The 3 parameters are free in this model, and it's a problem when we want to work with this model, fix them, and try to follow good results in order to describe some phenomena. Okay? Let me, before to explore this new idea, show some results that in collaboration with many people that is here, Alejandro Ayala, Marcelo Leve, Saúl Hernandez, where is Saúl? He's not here. Cristian Villavicencio, Ana Julia, and some others colleagues. We try to use this model, for example, to see what happened with the phase transition, the QCD phase transition. This is a QCD phase diagram, T versus the quark chemical potential. No, it's not, it's the baryonic chemical potential. And for example, here show 2 things, that we can reproduce the inverse magnetic catalysis, and we can reproduce or find a critical endpoint and how the critical endpoint moves as a function of the magnetic fields. The key ingredients in this analysis is that we compute effective couplings, corrections at what loop order to the couplings, and with that ingredient it's possible to reproduce this behavior or this phase diagram. That means that we go beyond mean field approximation, okay? And I highlight the values that we use for these free parameters in this work. This is the value for lambda, G, and A, okay? Please try to remember these numbers. And we report this work here. So the model works, reproduce qualitative very well what we know. This is a second result. One more time, we explored this QCD phase diagram, but in this case, without effective couplings, okay? The idea was improve the ring diagrams contribution. That is the way that we go beyond mean field approximation. And well, with this new contributions from the boson self-energy, we were able to reproduce very well the results following the curvature of lattice QCD, for example. Okay, but please look at this set of parameters that we use, completely different from the other ones. Okay, and if I remember well, these values were fixed in vacuum, taking into account the value of the masses of the degrees of freedom of this model, and we fixed these parameters. Okay. Another thing that we compute some years ago is the pole mass of the neutral pions in the weak field approximation, in the strong field approximation. Okay. We implement in our computation effective couplings in both cases. We fix the parameters in vacuum. Okay. Sorry, I forgot to put the numbers in this slide, but something that I can say is a different set of parameters that appear in each of these works. Okay. Another computation was the longitudinal screening mass for this neutral pion, where we are able to reproduce the lattice QCD results, and we use this set of parameters, lambda, G, and A, without effective couplings, okay? But in this case, we fixed these values using information with finite magnetic fields, sorry, okay? So in each of these works, we use a different set of parameters, and when we present our results, it's common that the people ask why you use these values, how do you fix? Is true that the values of lambda, G, and A is constant, even when you fix it in vacuum and you are working in other energetic region? Maybe that implies that we need to change the value of these parameters, and formally the answer is yes, should be the case that this constant change value as a function of the different effects, thermal effects, magnetic effects, on other effects that appears in the system. So as a summary of this first part, we have 3 parameters of this theory, and we need to determine the value of these parameters. For example, one option is these parameters are fixed in vacuum to take well-determined values using the values of the masses in vacuum, for example, the pion decay constant, or some other very well-known values, but we are not studying the vacuum, okay? We are in a situation far from that state. Another option is we determine the values of these parameters under the studied conditions. For example, in the case that I talked in the previous slide, at finite magnetic fields, finite temperatures, right? But we do not have enough physical information to determine them in that regions, okay? And the third thing is, well, the region under study is broad. That means maybe the parameters should not be constant, and we need to change the values. Depends where I study this, the dynamics of our system. Here, there are some other examples when we include not only a magnetic field, we include vorticity, we include effects of superstatistic, include many other different external effects. And well, the model and our techniques reproduce very well lattice QCD behaviors, how is the behavior of the critical endpoint as a function of these external elements that we put in our studies. Okay, so, but the question is, one more time, the problem of the parameters of this theory. So for today, let me show an effective magnetic QCD phase diagram. This is a work in collaboration with Ana Julia and Gabriela Hernandez, both here, and it's a work in preparation, soon will appear in archives. What is the thing that we can reproduce simultaneously is the inverse magnetic catalysis that we can observe if we analyze the light quark condensate as a function of the magnetic field, or if we analyze the pseudo-critical temperature as a function of the magnetic field, we observe this decreasing behavior as a function of the magnetic field of this temperature, okay? Another thing is we want to observe a critical endpoint. This is a work that Gregor and Dodi showed some years ago, and another study from the Italian group that shows more or less the same behavior, that really large values of the magnetic field, we find a critical endpoint, the crossover finish, and the first order phase transition starts at very large values of magnetic fields, right? So we want to put together these two features in the phase diagram and see if it's possible with this model. However, some years ago, Eduardo and colleagues shows that if we work with this kind of models, the linear sigma model coupled to quarks, and if we don't go beyond the mean field approximation, it's not possible to reproduce the inverse magnetic catalysis. We obtain good results because we go beyond, but maybe it's not the only way to go beyond the mean field approximation. So I will try to see that it's possible to find a good results in this new technique. Well, here is one more time the ideas about this model. We'll have this Lagrangian. It's the same that I present in the second slide, I think, or third slide. Here are the free parameters. We put the magnetic fields in this Lagrangian, change this partial to the covariant derivative. We use this gauge for this vector potential, and in order to observe this symmetry spontaneously broken, well, we allowed to do this shift in the direction of the sigma meson. And as a result of the shift, we rewrite our Lagrangian, okay? And we observe two important things. One is that appears dynamical masses in this Lagrangian that depends exactly of these parameters, okay, lambda, A, and G. And we can write a classical potential that in this case we also include an explicit term that breaks this symmetry in order to go to work with physical masses for this model, okay? So how is the computation? We need to compute the free energy beyond the mean field approximation. That means that we compute this free energy as effective potential, the classical term, one loop correction for each of the degrees of freedom, and we include the ring diagram. This is our first attempt to find both phenomena that we want to reproduce. Here is the expressions for each of these contributions. For the one loop contribution, we have the contribution for the neutral particles, the charged particles, both boson particles, and here is for the fermion particles. We use these propagators that, in the case of the charged particle, we use the lowest Landau level. However, for today and for the rest of the conference, please let me change a little bit the name. I will use the Latin Landau levels only for today. And this is the only approximation for the magnetic field. We work with this approximation, all right? Here is the expression for the ring diagram that are very important to take into account this screening phenomena in the dynamics of this theory. Here I present all the contributions for the self-energy that are included, here in the terms of the ring diagrams. The expression, I don't want to show any explicit computation, only the results that you can see how it depends on temperature, magnetic fields, how appears the masses, and look at some curious terms. For example, this one, okay? This is the root square of m sigma square. But if you remember, m sigma square is this expression, okay? Imagine if you take v equal to 0. That is negative, and that provides an imaginary term, okay, in the free energy. So there are some troubles here in this model when we work with small values of v. Okay, here is the effective potential. One more time, for example, here we will have some problems, or maybe here when the mass is not positive defined, okay? Maybe here. And well, we try to analyze what happened with this expression. And well, we try to follow the behavior of the minimum of this potential, the vacuum expectation value, that is the order parameter in this theory, to analyze when the symmetry is restored. If you see, well, for a small, well, for the smallest values of a magnetic field that we took, we find a continuous behavior of this vacuum expectation value that tell us that is a crossover. And when we increase the magnetic field, at some point we observe this jump that tells us that appears a first order phase transition. But other thing is that the critical temperature, looking this plot, increases as a function of the magnetic field. Okay, this is the values of lambda, G, and A that we use, fixed in vacuum. And how looks like the phase diagram? Well, this is the behavior. We observe that, okay, appears a critical endpoint, but we don't observe this inverse magnetic catalysis. Okay, so that it's the motivation to try to tackle one more time the problem with another point of view. Before to show these new ideas, let me show what happened with the potential with the problem of this definition of the masses. If the mass is negative, at some point we cannot plot completely the potential, okay? That is information that we are missing, and maybe it's important to see that region, because sometimes when we need to analyze the first order phase transition, we need the complete information of this potential, right? Okay, well, a new alternative, we will allow all the free parameters of the theory to become variable, but without a functional form for each one of them. I don't want to see how change lambda, A, or G as a function of V or T or some other external variable. Actually, I will analyze the behavior of the masses as a function of these parameters and as a function of the V variable that describe the shape of this potential, this V that appears here, okay? So the idea is to build a system of coupled equations, okay, self-consistent equations, where I want to find how looks like this function as a function of T, V, and of course of V. For each of these, I will find the solution, okay? I have 3 equations here, okay, for the sigma, for the neutral pion, for the charge pions. Here are the expression of this self-energy without any approximation. We sum over these infinite terms. We integrate over all of this domain, okay? And we try to solve these self-consistent equations, okay? So now we have this effective potential, okay, that I cannot write explicitly because everything is numerically, okay? But instead of having this expression for the masses that I call the 3-level masses, now I will put the solution of this equation in the potential, okay? The first thing that we found is we can able to plot completely the potential without any problem, okay? From 0 to any value. For any temperature, for any magnetic field, we reproduce here how the temperature helps to restore the symmetry. A very low values, well, in this case, for some values of temperature, see the effect of the magnetic field, okay? So now we are able to reproduce completely this potential, but not only that ingredient is new. The thing is, when we look at this vacuum expectation value as a function of the temperature for different values of V, we find something really good, that these curves have a common place where they cross each other, and this is a signal for the inverse magnetic catalysis. That's beautiful. Well, for us, was a really good result. Also, we can find some regions where the magnetic field is large enough to find this first order phase transition. For example, if we follow the behavior of these dots, now we observe a jump here, okay? And we fixed the values of lambda, G, and A in vacuum, but remember, I didn't use the expression of the masses in terms of these values, okay? And how it looks like this phase diagram? Well, we observe the critical endpoint, okay? And we observe the inverse magnetic catalysis as well. This is, I think it is a unique result with these new ideas. And well, this is like a new stage when many of my collaborators are very happy to come back with old problems and tackle one more time and see what happened and look at for new analysis, new problems to try to solve with this model, okay? So for future work, well, we need to compute all the contributions for all the self-energies. I didn't mention anything about the fermionic case, okay? That is not easy to compute. That is the truth. We are working on that self-energies. One thing is, in order to find the solutions in terms of three parameters, T, V, and V, this V, okay? Well, we have a lattice. So the way that maybe it's possible to go in the continuous limit is using artificial intelligence to find the analytic expression in terms of these variables for these masses, okay? And of course, in the case exactly of this example that I present today, we need to recompute our analysis without any approximation. We can sum over all the Landau levels or take the Schwinger propagator and compute everything and see what happened in the full range of the magnetic fields. So, as a conclusion, in the linear sigma model, the masses should capture the collective effects of the medium without any restriction, okay? And it allows going beyond the mean field approximation in a proper way, generating consistent results. Another important thing is that this model is successful in exploring different phases diagrams of a strong interaction, not only with magnetic fields, it could be with baryon chemical potential, isospin chemical potential, with vorticity, with many other ingredients, okay? And we can implement a systematic study of the strong phase transition and see what happened with these other new ingredients. And of course, we can remove many assumptions that we did in the past when we compute many of the results that I showed today. Okay, well, that's all. Thank you for your attention.
So we have one question here.
Thanks, Luis, for the talk. What is the difficult to do related to evaluate the fermion mass that you say that is difficult?
The charge part is a charged particle. Many of the Feynman diagrams that we need to compute at one loop includes the Schwinger phase, and we
but
need
including the charge mesons, right?
Yeah, but only at lambda order. That is is not complete the self-energy for that charge particles. That's true. That's the other thing that we need to compute. Yeah.
Did you compare the pion mass with this approach with the lattice?
We didn't, but we can do.
Thank you.
Any more questions? Comments?
Thank you, Luis, for a nice talk. I have a question, because you relaxed the functional definition of the masses in your approach in order to reproduce the potential. But then the question is, what happens with the coupling, for example? I mean, can you still retain the definition of the renormalization of the coupling and the VEV, the V, the vacuum expectation value is a function of the magnetic field? Is that retained or not? That's it.
Yeah, very good question. Well, for this set of equation, this value, this lambda, and well, in the case of the fermion term that is not right here, lambda, A, and G is fixed in vacuum, and all the information from the medium is in this self-energy. But this is a really good question. What happened with the couplings? For example, the ones that appear here, okay, is in vacuum or not? That is a good discussion. If we can go or take more contributions in this way. Yeah, but for this work are fixed, no? And the information of the masses is not longer the definition of the three-level masses that I showed. It's not more dependent on lambda, G, or A. Okay.
Okay, so in a sense, you're retaining the bare definition of lambda and V in your formulation, but you're redefining the masses. That would be the...
Yes, include by this self-energy, all the information of the media.
Yeah, and then a final comment. Is it possible maybe to think in terms of an RG flow of these couplings, in terms of the magnetic field strength?
That is another way. Yeah, it's the most formal way to
beta functions for every coupling.
Exactly,
right?
exactly. Yeah, that's the point. I completely agree. If we want to do in a most robust, it is the only way to see the real effects.
Thank you.
At each order.
Now, just a comment about your question, Enrique. The point here is that Eduardo showed years ago that in the linear sigma model, even if you consider Polyakov loop or whatever, you can play in the way you want with the parameters. You can make them functions of temperature and magnetic field, and you never get the lines crossing. So, I mean, it's there. So what we showed is that if we go beyond mean field, then we can have those lines crossing, meaning that we can reproduce inverse magnetic catalysis. So we still have to study what is the optimal way to write couplings and whatever constant, whatever parameter in terms of B or temperature. But what we show is that it is possible. So if it is for years, people thought linear sigma model couldn't do that. We show that, yes, I mean, if you do in this way, including ring diagrams and self-consistent masses, then you can get these results. But of course, there is a lot of work to do.
Okay, any other questions or comments? Okay.
So thank you for the talk. I'm a little confused by this new scheme. So I'm not sure if you still make contact with the vacuum. That is, if you still reproduce the correct masses that we can actually measure in the vacuum when you set B and T to 0.
Exactly. Here, if we take T equal to 0 or V, all of this contribution disappears, and we recover the expression where lambda, A, and G reproduce or are fixed in terms of the vacuum masses.
Right, so then lambda, A, and everybody is already fixed a priori so that you recover the vacuum.
Yes.
So they're not free to run or anything. Okay.
Just a quick comment, which also touches upon what I commented before with Javier's talk. so to make it more evident, those lambda A and G that is not there, it's because Luis didn't, Ana Luis didn't study the fermion mass or included the fermion mass in their analysis, but those are the vacuum ones. But then when they solve the problem for the dynamical masses, this is the capital letter masses, then what will happen, or what happens, is that if they write those masses in terms of new couplings, lambda prime, A prime, G prime, and the vacuum expectation value of the order parameter that is obtained from the gap equation, from the one loop potential, then by preserving the form that is required from the Lagrangian, that is that the, for instance, the pion mass squared is going to be lambda prime B prime squared minus A prime squared, then that shows already that since the masses, the dynamical masses are changing, then the parameters themselves will change. So starting from vacuum values, they will evolve with the external parameters. And that is something that I think it's very appealing, because it is a way of self-consistently compute those changes, as opposed to other approaches in which you need to do something else outside from the model, like guessing for instance, in the NGL model, guessing some form that reproduces lattice results or so. So this is interesting to see, Luis, that you guys obtain inverse magnetic catalysis from that approach. It will be very nice to extend it to arbitrary values of the magnetic field.
All right.
Just a comment.
Thanks.
Okay, so let's thank the speaker again. And now I think we have lunchtime, right?